My name is Roger. I work for Citrix on the open source team, and I mainly work with the Xen project together with other projects like the Linux kernel or FreeBSD. And I'm here today to speak about Xen and the new features of the last version that we released. Last week we released a new version, that's 4.6. And I'm mainly to speak about the new version here. First, I will do a small description of Xen. Some of you, I guess, already know Xen or have used it. Can you raise your hands? Well, yeah, not bad, I guess. Then I will speak a little bit about the community, how we work, how we develop Xen in general, and then we'll go into the new features of the later release. So first of all, people attending the CentOS Dojo yesterday already saw these slides, so nothing new here, but I like to usually start with those because it's an overview of how a Xen system usually works, which is kind of different to type 2 hypervisors. Here we have the hardware on the bottom, that's the hardware that we're going to run on. Then on top we have the Xen kernel, which is a microkernel. And then on top of the Xen kernel, we have what we call the control domain. This is the first guest that's created by Xen when it boots, but it's a guest. It's a guest with some special privileges because it's able to create other guests, it's able to interact with the Xen hypervisor itself, it controls the hypervisor, but it's also just another guest. And then we also have other guests running here. And I like to also represent some tasks that usually run inside of the control domain, like usually have syslog, you have terminals, you may have X11, or, well, I don't know, whatever application you want to run. And then if we look at the architecture of a type 2 hypervisor, we can see that it's quite different. Here we have the hardware. Then on top of the hardware, we have the operating system. And the hypervisor, its bundle itself inside of the operating system. And then on top of the operating system, of course, we have our task that we saw on the other slide also. And then we have the guests that are running inside of the system. I would like to notice that on a type 2 hypervisor, for example, guests compete with tasks running inside of the control domain or the host in order to get resources. On the other hand, on a type 1 hypervisor, tasks inside of the host are completely isolated from other guests. They don't compete for resources, for memory, for CPU power, for anything like that. This is quite different. The main examples of type 2 hypervisors are KVM, VirtualBox. I think VMware Player or something like that is also kind of a type 2 hypervisor. And then, well, I will go a little bit fast over this because it's not really interesting, it's just a little bit of background. Xen was designed in the late 90s. By that time, there were no hardware virtualization extensions. It was a project that was done together with the Cambridge University, Intel, and Microsoft Labs. And they basically realized that x86 was not easy to virtualize. The architecture was not designed for virtualization. So the only two options that you had were either full software emulation or binary translation. They realized that both of those were quite slow, so they designed a new interface that will be used for virtualization. Designing a new interface means that each guest that you want to run needs to be modified in order to use this new interface, because it's no longer the same interface that you have on bare metal. It's a completely different interface. So basically, you have to modify each guest OS in order to run under this mode that's called para-virtualize or PV. And basically, they decide that a bunch of things need to be para-virtualized. Of course, the disk and the network interfaces were para-virtualized in order to obtain better performance, but also the interrupts and the timers were para-virtualized. The way the kernel boots is different than on bare metal. The page tables are also para-virtualized. If you want to modify page tables, you need to issue hypercalls into Xen that will modify the page tables on your behalf. And also, you need to issue hypercalls in order to execute some privileged instructions. Then, with the introduction of hardware virtualization extensions, Xen was able to run unmodified guests. We usually call this unmodified guest HVM guest. And these kind of guests require a QEMU instance in order to provide the emulated devices, like the emulated network card, the emulated disk, the emulated local AP, quite a lot of those things. Some of them are handled inside of Xen directly. Some of them are emulated by QEMU, but there's quite a lot of software emulation when you run unmodified guest. And also, we have a new mode that was introduced quite recently. It's only for x86, and we call it PVH, which is basically a mix between both modes. This will sound a little bit strange to you right now. I have a slide. The next slide is probably going to be easier to understand. But basically, we have PV, we have HVM. Both have its strong specs, and we wanted to do something that merged the best of both worlds. And we decided to call it PVH. And it's basically a guest that makes use of PV interfaces when they are fast. Otherwise, it makes use of hardware virtualization, basically. The original design was done by Mukay Rathore at Oracle, and then quite a lot of us from Citrix continued developing it. So this is the full virtualization spectrum that we have on Xen. These are the kind of guests that we support. Here on top, we have HVM, which uses software virtualization or software emulation for mostly everything, except for the privilege instructions and the page tables that are virtualized by hardware. And then on the other end, we have PV guests that use para-virtualized interfaces for everything. As we said, PV guests, for example, use para-virtualized interfaces in order to interact with the MMIU. This is very slow because every time you have to modify a page table, you have to issue an hypercall into Xen, and well, it takes kind of a long time. So this square is orange because it means there's some room for improvement there. For example, HVM guests have hardware emulated MMIU, which means that we don't need to do anything. It's all done by the hardware, and it's much more faster than issuing hypercalls into Xen every time you want to modify a page table. And then in the middle, we have guests that make use of different features. For example, we can have an HVM guest with PV drivers. We can have a PV HVM guest, which uses PV drivers for the disk and the network card, and it also uses PV interfaces for the interrupts and the timers. And finally, we have PV HVM, which is this new mode I've been speaking about. And PVH mainly uses PV interfaces for the disk and the network, of course, for the timers. It also uses, and then it uses hardware virtualization for the page tables and the privilege instructions. This allows us to get the best performance of all the different modes, and we expect that this mode is going to bring quite a lot of performance improvements to Xen. So a little bit about the community. The Xen hypervisor was released under the GPL2 in 2003. And then in 2013, it became a Linux project, a Linux Foundation collaborative project. And we also have several sub-teams inside of the Xen project that focus on specific topics or specific features inside of the hypervisor. For example, we have the main team, that's the Xen hypervisor. We also had another team that worked on porting the hypervisor into ARM. This has now been merged upstream, so the team is no longer active, or well, it's merged into the Xen hypervisor team, basically. We also had the Zappy team, which was a different tool stack for the hypervisor. We also have another team that's working on Mirage OS. Mirage OS, I don't know if many people is familiar with that, but it basically allows you to compile OCaml applications into kernels that you can run on top of Xen without needing any kind of operating system. You can just pick an application, compile it as a kernel, and put it on top of the hypervisor itself without needing anything else, which is quite interesting, but you need to write them in OCaml. And then we also had the PVOps project, which focused on adding Xen PV support to the Linux kernel. This is already finished, and the Linux kernel, starting from 3.0, which is maybe 5 or 6 years ago, all came with Xen PV support inside. What else? Yeah, the governance, it's quite similar to the Linux kernel in a sense. We have several roles. For example, we have the maintainers that take care of one or more components inside of the Xen tree. For example, we have maintainers for the tool stack. We have maintainers for the x86 bits. We have Intel-specific maintainers that take care of Intel features, the same for AMD. Then we have committers, which is a subset of the maintainers that have write access to the repository. They basically pick patches from the mailing list that are acted by the relevant maintainers and commit them. And then, as said, we also have the sub-project teams, which are teams that do projects related to Xen itself, although they may be based on the Xen code or not. And we also have quite a lot more information on the following page. The Xen hypervisor, which is, of course, the main project, has 6 committers, actually. So this number, well, the rest of the sentence is fine, but it should write 6 committers. We have committers from quite a lot of different companies, like Citrix, SUSE. We also have one committer from Oracle, and we have 2 committers that don't belong to any organization at all. And during the 4.6 release cycle, we have 96 contributions from 30 different organizations. And the companies that contributed more to the project were Citrix, SUSE, Intel, Oracle, Linaro also contributed, and Fujitsu also. You can find the full list on the following wiki page. I'm not going to list them all because there are a lot of them. So, about the new features of Xen 4.6 that we released 1 week ago, we have improved the memory event subsystem. For those of you who are not familiar with the memory event subsystem, it basically allows you to set a specific, it allows you to set callbacks on a specific event. For example, if a guest modifies a memory page, if it tries to write or read from a memory page, if it tries to access a specific register, things like that, you get traps, and you can process that on your control domain. This is especially interesting if you want to do things like memory introspection or figuring out what the guest is doing without interfering with the guest at all, because you don't need to install anything inside of the guest. This is all done on an hypervisor level, and is used by quite a lot of companies that work on antivirus and this kind of software. For example, you can set specific traps on memory pages that are used by Windows, and you can detect when an application is trying to write to the kernel memory space. You can do this kind of stuff, which is quite helpful. And you don't need to install anything inside of the guest. It's all done on the hypervisor level. Then we also improved the default XSM policy. XSM also, for those who don't know, it's something very similar to SE Linux for Xen. It's a control access system, mainly, that's implemented inside of Xen. And we added a default policy, and also we test it regularly to make sure it works fine, so people can use it without having to write their own policies or anything like that. We also implemented support for TPM version 2.0. And the last 2 improvements are mostly related to performance. We improved the grant table scalability. The grant table is used to share memory between domains, so you can have shared memory regions between several domains or between a domain and the control domain. And we also improved the log mechanism in order to use ticket logs instead of spin logs. This is better because it gives you more fairness. It means that each guest, each time you try to pick a spin log, you pick a ticket, and then you go, you follow a certain order. So it's first come, first serve, basically. On x86, we have quite a lot of improvements related to Intel processors. We added support for something called alternate P2M. This allows you to switch the second stage translation of guest using several tables. This is something very specific to Intel, and it's also used for memory introspection, basically. We also have page modification logging done in hardware. This is interesting when you do migration. The process for migrating a guest is you usually detect if a guest has written to a memory page and migrate this memory page. This used to be done in software in the past. Now, if you have hardware capable of doing it. You can do the page modification logging by hardware. We also have some improvements related to cache allocation and memory bandwidth monitoring. These are also features found in new Intel processors, which allows you to track guest memory and cache usage. This is interesting for mainly load balancing the guest inside of your host. We also added support for profiling Xen itself using performance monitoring counters. This is something also found in hardware. And finally, we introduced a way to provide a guest with a NUMA topology. This is interesting because if you have a NUMA box, usually when you create guests, they don't know anything about the NUMA topology behind the box, the real topology. Now you can pass certain parts of this topology to the guest. For example, you can create a guest that has memory allocated on 2 different NUMA nodes and provide that information to the guest. This is really interesting because the guest knows that it has memory on 2 different NUMA nodes and it will try to use it accordingly. We also had quite a lot of ARM improvements. We improved the number of vCPUs you can use for guest from 8 to 128. This is only on ARM64. On ARM32, we are still limited to 8 virtual CPUs, but I don't think there are any ARM32 boards with more than 8 physical CPUs. We also allow pass-through of non-PCI devices to guest. We improved the support for the interrupt controller. We also added support for booting ARM guests using UEFI. And we also support guests that use 64 kilobyte pages on ARM, which is, I think, the default on CentOS now. On ARM64, they are using 64 kbit pages. And finally, we also added support for a bunch of new platforms. Then we also had some tool stack updates. We reworked the migration stream protocol that's used when you perform live migration of VMs to what we call migration v2. There has also been quite a lot of rework of REMOS, which is the high availability solution for Xen on top of migration v2. We improved the support for SPICE and QXL. And we also merged the Xenalize into the Xen code base. Xenalize is something that you can use to trace guests and know what they are doing. It used to be a different project that had its own code repository, and now it's merged inside of the Xen code base. We also moved to a new test lab in order to have all of our test infrastructure. It was funded by the Xen Project Advisory Board, and currently it has 24 dedicated machines. It's a mix between Intel, ARM, and AMD boxes in order to do a full coverage test. We try to have very different hardware in order to test all possible solutions. And every commit that goes into Xen is tested against this lab to make sure it doesn't break anything. And then, related to other operating systems, we had some updates on Linux. We added multi-page support to Blockfront, which is the para-virtualized block driver for Xen. We also added support for Xen iSCSI, which is another para-virtualized protocol that you can use on Xen. We did, of course, several performance improvements, and we expanded the memory supported by PBGuest up to 512 gigabytes. On FreeBSD, we added support for PBH DOM-U and DOM-0. We removed a very crappy 32-bit PB port that was there but was not working. And there was also an implementation of indirect descriptors for Blockfront, which increased performance quite a lot. Oh, sorry. So, in general, the 4.6 release, we considered it one of the best releases so far. We had very good code quality. We didn't catch almost any bug in the Xen test system, which means that the commits that were inside were of very high quality. And we also saw an increase in the number of contributions, especially from different companies and different people. In the past, we used to have maybe a more smaller community. Now it's getting quite bigger and more diverse in general. And it's also important to notice that this was the first release that was completely on time. Well, it was ready 1 week before, but it was quite interesting because we usually used to delay 1 week, 2 weeks, maybe the release. This time we were very, very on time. And that's mostly everything I had. If you have questions, I don't know if you want to do it now or we move to the next.
Yeah, well, we can take a quick question. Or, I don't know. Does anybody have any question for Roger? Yeah.
Just going back to your table of red and yellow and green things, we noticed that Amazon has pushed very hard to push their people into HVM. Do you think they're using the HVM with PV drivers underneath? Or
That's
the
something
PV
that
HVM?
That's something that's completely up to the guest. It's not something that Xen decides. You create an
You
HVM
can't tell.
guest.
You can't tell which one you have when you're inside the guest.
No, they always have PV.
We always provide PV drivers. I mean, all these guests from a Xen point of view are exactly the same. You don't need to add anything to the configuration file or anything like that. It's just a matter of what the guest OS kernel supports.
Well, once you get above Red Hat 6 and above, of course.
Yeah, Red Hat runs as a PV HVM guest because it's using the Linux kernel.
Okay.
So unless Red Hat decided to remove that support, it will run as a PV HVM guest.
Hi, I'm a generalist, so be generous with me. There's a couple of companies out there who are working on something called TCP/IP stack acceleration. A company called 6Wind is like DBDK related. Yeah, but basically their thinking is the existing TCP/IP stack is a poor match for virtualization. Could you just comment on that?
I don't really work on networking, but I think there are some issues mainly with the window size or something like that, because since VMs are scheduled in and out, you can sometimes takes a little bit of time to get ACKs back, and then the window is gone and you have to resend the packages, I think, or something like that.
Okay.
But at the end, you don't really need to use TCP/IP inside of VMs. We just provide a virtual network interface, and then you can use whatever protocol you want.
So for you, it's a separate domain altogether. It's not part of the virtualization.
No, there's no TCP/IP specific code inside of Xen.
Okay.
I mean, Xen just provides an interface with a specific protocol, and then you send packets over it.
Okay.
But yeah, there's nothing TCP/IP specific about it, I think. You could use any protocol. You can use ICPM or anything like that.
Okay.
But yeah, generally you have to use TCP/IP because that's what people use. I mean, there's no much you can avoid there.
On that note, 6Wind and others are in the business of identifying areas where free software is lacking something, making a proprietary product to fill that niche and integrate it quite nicely with the free software community, so that they are perceived as good players, where in reality they live off something that if it disappeared, their business model will also disappear. So they have a vested interest in keeping this problem alive and not solving it. That's part of the reason why it exists.
Thank you. So maybe we can move on to the last session.